Next, we are going to consider how our secular theory for two bodies can be expanded with the introduction of an infinitesimal mass to that three-body system. So we're going to take our existing structure where we have a central body M1 and two much smaller bodies M2 and M3, and we will add a fourth body, M sub p, whose mass is negligible compared to the masses of M2 and M3, which makes it really negligible compared to M1. So the mental picture here is the Sun and Jupiter and Saturn and an asteroid, for example. The disturbing function on our particle MP is given by this expression here, which has a very, very similar form to the disturbing functions that we wrote for bodies M2 and M3, but now includes the effects of both of those bodies. In this case, any orbital elements that do not have subscripts should be treated as the orbital elements of the test particle. So this A, E, I, and var pi and capital omega are the elements of body MP. Everything else that does have a subscript, this E sub j, this I sub j, this var pi j, and capital omega j, should be treated as the orbital elements of body J, where J is going to be either 2 or 3. We will define new coefficients, A sub p, B sub p, A sub j, and B sub j in this form. You will notice that there are some Boolean operators floating around in these exponents. The way to interpret these is as a integer valued 0 false, 1 true. So if A sub j is less than A, that is, if we are looking at body 2 and its semi-major axis is smaller than the semi-major axis of our test particle, then this is 1. And if we're looking at body 3, for example, and its semi-major axis is larger than that of the test particle, then this evaluates to 0. Same here. If A sub j is greater than A, this is 1. If A sub j is less than A, this is 0, and so on. If you prefer, you can also just write these expressions out with cases or if else, or however else it helps you to think about this, but that is the way to parse these equations. As always, you are strongly urged to attempt to recreate the solution based on the same procedure that we followed previously. We are taking the disturbing function for this body due to two other bodies. We are expanding it in second order and then averaging. We are once again going to use our transformed coordinates, C, D, U, and V. These are, again, without subscripts, interpreted as belonging to the test particle. And we can rewrite our disturbing function for the test particle in terms of these coordinates, and it has a form exactly like the one that we've seen before. The resulting differential equations, from applying the first order linearized Lagrange planetary equations, take the exact same forms as before. C dot and D dot are both 1 over NA squared, N being the mean motion of the particle, A being the semi-major axis of the particle, times the partial of the disturbing function for the particle with respect to D, and negative the partial of the same disturbing function with respect to C. We can once again write this as a linear system, although in this case it has a slightly different form. We will have this single AP scaling D and negative C plus matrix D2, D3, negative C2, negative C3 times A2 and A3. We already have the solutions for C2, C3, and D2, D3 from our previous analysis. The test particle has negligible mass and therefore cannot affect the orbits of M2 and M3, and so these solutions stay the same, meaning that we can plug in the solution from our eigendecomposition of the original APP matrix back into here, and you will recall that those solutions have these forms. We have cosine and sines of lambda 1 and lambda 2t, where these were the eigenvalues of the original APP matrix, plus alpha 1 and alpha 2, which were given by the initial conditions of a particular system, times the normalization of the eigenvector matrix. And in this case, it's all transposed because that is the form that this matrix takes. The same exact thing holds true for the differential equations in U and V for the particle. We can once again write them as a linear system, substitute in our solution from the secular theory for just the two bodies M2 and M3, and get this expression. Rather than attempting to integrate these expressions, we are instead going to differentiate them. The reason being is that we are going to come up with some very familiar looking forms if we consider the second derivatives of C, D, U, and V. Let's take a look. The second derivative of C and D will be equal to negative AP squared times C and D minus this matrix of sines and cosines from the secular two-body solution of bodies 2 and 3 times the transpose of that normalized eigenvector matrix F times A2 and A3. And the exact same form holds true for the second derivatives of U and V. These are fully decoupled equations with known solutions. C will be some constant that we call E free, that is a function of the initial conditions of the system, times the sine of AP in time plus alpha p, where alpha p is once again a phase determined from initial conditions, plus the initial value of C naught in time. D has the exact same form with the exact same amplitude and phase and period, save that it is cosine, and U and V follow the exact same pattern, save that they are in inclination and have a coefficient of the free element of the inclination times the sine and cosine of the same period and phase, with the phases determined by initial conditions plus an initial offset. These initial offsets, C naught, D naught, U naught, and V naught, are given by these matrices, which are functions of the solution to the two-body secular theory for bodies M2 and M3. The key thing here is that all of these initial offsets, the C naught, D naught, U naught, and V naught, are functions of the semi-major axis of the particle, which is embedded in AP and BP, and none of its other orbital elements. What we found is that we can trace the evolution of this particle essentially based on where it is initially located in space. On top of this, we will define forced components for the eccentricity and inclination, given by the root sum square of that C naught and D naught and U naught and V naught, respectively. And we will define longitude of periapsis free and longitude of the ascending node free, defined by the arguments of the sinusoidal functions in the solutions. So how should we interpret all of this? Our test particle has some osculating orbital elements, and then it has these free and forced components of orbital elements that we've defined via this process. The geometric interpretation of these definitions is that our particle is going to travel about a point C naught and D naught in the CD plane, which you will recall is given by E cosine var pi and E sine var pi, at a constant rate of that AP coefficient. The true osculating eccentricity will be at an angle var pi from this C component, and this var pi free angle, measured from also the line parallel to the C line, gives the orientation of the E free component, from which you can reconstruct the E forced component. The center of this is that C naught and D naught point, and our actual eccentricity is orbiting that C naught, D naught point at a constant rate given by AP. And the exact same thing is true for the inclination. The particle's true inclination orbits in the UV plane, alternatively the I cosine omega, I sine omega plane, at a constant rate BP about the 0 point U naught, V naught. It's important to note that neither of these paths necessarily encircle the origin. These are arbitrary renderings from Murray and Dermott. In this case, the relationship with E free being larger in magnitude than E forced, and in this case, I free being smaller in magnitude than I forced. But the actual locations of these paths are given entirely by the specific initial conditions of the system. The reason for the nomenclature is that the forced parameters are functions of the particle's semi-major axis and the secular two-body solution only. No other particle elements matter in determining the forced parameters. The free parameters are functions of the particle's initial condition and are a fundamental measure of the particle's own orbit. And for this reason, they are also known as the proper elements. This is a reproduction of a numerical example from Murray and Dermott, originally figure 7.7 in the textbook. And this is showing the results of numerical integration for 250 test particles along with Jupiter, Saturn, and the Sun over a period of 30,000 years. capital C naught here represents the location of the original C naught and D naught, and in this case, the initial location of U naught and V naught. And C1 represents the location of those points at the end, 30,000 years later. And we see an exact confirmation of what the equations told us. We have rotational motion of the components of the eccentricity and the inclination about these center points, while the center points themselves travel through the plane. As previously stated, all of this development can be applied to systems of n bodies. All that's needed is to add all of the mutual secular perturbation. Therefore, in the n-body case, the matrices A and B that we previously defined that were 2 by 2 are now n by n for n orbiting bodies, meaning that you have n eigenfrequencies, equivalently eigenvalues, and n eigenmodes. The secular theory for the solar system was first developed in Brouwer and van Woerkem, 1950, with results reproduced in Murray and Dermot, figures 7.9 and 7.10. This theory includes 8 planets to second order, along with 2 eigenfrequencies to capture the near resonance between Jupiter and Saturn that we've already stumbled across, that near 5:2 configuration, and large terms from a higher order secular theory, plus the oblateness of the sun. Therefore, this theory contains 10 eigenfrequencies total, and the A and B matrices are of dimension 10 by 10. And these are the predictions of this secular theory for the eccentricities of the various planets of our solar system. This is showing the variation over 10 million years, centered on AD 1900, so roughly 5 million years into the future and 5 million years into the past, from now, give or take a century. And we see things that are very comparable to what we get out of direct numerical integration of the n-body system. We have many periodicities, but fairly small excursions in the eccentricities of the orbits of the inner planets. And then we have very tight coupling with higher order and lower order periodicities for Jupiter and Saturn, and large bulk effects on Mars, primarily due to Jupiter, and then very, very well-behaved periodicities for Uranus and Neptune, with only the hint of second order effects being visible. For 1950, where the kind of numerical integration that we now take for granted over millions of years on our own personal computers was literally impossible, this was an amazing accomplishment. And even though it is now still way, way simpler to code up a numerical integration than it is to go through the painstaking labor of constructing these solutions, they are still incredibly valuable because they provide almost the only independent check possible on those numerical integrations. They allow us to build confidence in what the computers are doing and give us a handle much more directly on specific effects that we would otherwise have to tease out of the outputs of the numerical integrators. And so even though we now have a much wider array of computational tools in hand than were available when this theory was first developed, they do not supersede this theory. They heavily augment it, and they are incredibly helpful, but it is very much worth our while to still think about secular and resonant theories of the solar system when thinking about its long-term numerical integration. We plot the same things for the inclinations and again see very similar effects, many of which can be qualitatively, if not necessarily exactly quantitatively, recaptured through direct numerical integration of the n-body model of the solar system. Just as we can generalize the secular theory to n-bodies, so too can we generalize the concept of free and forced elements. In this case, where we have test particles interacting with n other major bodies, we will have those AP and BP coefficients defined as summations of all of the major body contributions. When we do this, we find a fascinating thing. Asteroids cluster in families of their proper or free parameters. And this is what is being showed here. These are the proper eccentricities and proper inclinations plotted against semi-major axis for a large number of various asteroids within the solar system. And we see clear clustering. And this is what allows us to define asteroid families. Even though the actual asteroids belonging to these families are scattered throughout the belt, and their modern actual osculating orbital elements vary greatly from one another when we isolate their proper elements, the ones that are functions of only their initial conditions, rather than those imposed on them by the major bodies of the solar system. We see this very clear clustering, and this gives us direct evidence for collisional origins of these families. This is a really good visualization of the fact that it is likely that in the past there were larger bodies that smashed into each other and gave rise to these families of asteroids that were then scattered both by that initial collision, but more so by the perturbations imposed by the major bodies of the solar system. This was first described all the way back in 1918 by Hirayama, who analyzed the orbits of essentially all of the asteroids that were known at that point, or had sufficiently good measurements such that these derivations could be carried out. And one of the key things that was shown in this original work is that asteroids would tend to cluster into groups when you plotted their semi-major axis versus their eccentricity and their semi-major axis versus their inclination. But that clustering was way, way more pronounced when you were plotting the free or proper rather than the purely osculating elements. Hirayama was the first to propose that each such cluster, subsequently called family, represented an object that had a common dynamical origin, and that most likely what we were seeing was a result of a breakup of a single large originating body or parent body. Subsequently, it became customary to name each of these families after the largest object belonging to that family, and these are the names that you see here. Anytime a new asteroid is discovered today, as soon as there's sufficient data, its proper elements are calculated, and most frequently it is assigned to an existing family. Approximately half of all known asteroids are thought to be members of one or another family. Murray and Zermatt also plot the osculating values for all of the asteroids shown in these graphs. And so here we have the C and D components and the U and V components for all of these. And we can see, if we squint just a little bit, clear evidence of rings within these structures, much more clearly seen in the UV plot. This matches incredibly well to the analytical theory that we developed that predicted exactly this kind of circular behavior for things that had the same dynamical origin, the same basic initial conditions.